It's pretty much impossible to brick the iPhone because of this process, because you can, at any point, brick the applications processor, that is. At any point, because you can always bootstrap the restore process like this. Okay, so the way that this restore process is protected is that iBoot that's loaded from any stage is signature checked before being executed. The RAM disk and kernel are also signature checked by iBoot. And restore D itself signature checks the ASR image and the NOR firmware. And restore D sits on a signature checked RAM disk, so it itself cannot be normally modified. Also, everything is encrypted with something with a key that's derived from a hardware AES key. This AES key, we can't read it, but the code on the iPhone can use it. These keys are disabled from a non-secure boot, from any boot that's not from a signed RAM disk. So this means that even if we were able to find a code execution exploit in userland on a normal boot and have a privilege escalation exploit and communicate with the kernel and try to tell it to flash the NOR, we still can't do it because we're not in a secure mode. The file system itself is encrypted with File Vault, and the way that's done is the File Vault key and also the expected SHA hash of the file system is stored on the encrypted RAM disk. And this way, everything is encrypted, and it makes it difficult for us to do our work because we can't read any of the code and we can't reverse engineer it. So that's the way that they planned it. So it still sounds pretty secure. All the modification this graph shows all the modification vectors for every piece of the software that I mentioned. And you see that everything signature checks everything else, pretty much. So it's still pretty secure, even if the boot ROM doesn't signature check LLV, as long as you can't modify a NOR. Well, there's one problem, and is that this chain can be broken, and what better place to break it is than at the boot ROM level, where they can't patch it or fix it in any way. So it's pretty much your standard stack exploit, stack overflow exploit. They store, as they're processing the certificates, which are in a DER format. They copy all the certificate information onto the stack, but the signature itself is copied into this data structure without any sort of bounds checking. So then you have this classic stack buffer overflow, and then you just make the signature checking function return true. So I'm just going to show you, I probably don't have enough time to do a very thorough job of this, but basically this is the function that we want to return true. We want to jump to offset 57EC and make R4 1, because R4 gets moved into the return value later. Check certificate and get secure boot ones is the function that has the vulnerability. As you can see, in the highlighted areas, it makes space on a stack for 3 certificate structs. So these certificate structs, so what you want to do is construct a certificate DER that that's structured like this. There's the padding to fill out the thing that's overflowable is cert signature value. So you have 0x30 bytes of padding at the end to cover the rest of these, and then you can start loading the registers with your own exploit values. So 1 for R4, we don't really care about the other registers, and the offset 57EC for the PC, for the program counter. So that's basically our exploit. So what we use to do, what we load from this is what we call pwnage, which is our complete solution, as it were. What we do is we patch every single stage, like where I mentioned all the signature checks, we patch all of those out. And what we do, we patch it out in the LLB, iBoot, kernel, the restore D on the RAM disk, and on the file system image, because we patched out the signature checking on restore D, we can put our own sort of app store for unsigned programs, for things that Apple won't support. And the 2 most popular ones are Cydia and Installer. So we use iBoot we use the DFU exploit to load version of iBoot that doesn't perform signature checking, and then we use a normal restore process to restore the rest of it, to flash the rest of this onto the iPhone. And what ends up happening is that we can use iTunes to flash our own custom firmware onto the iPhone. So, yeah. So just briefly, I'm going to just mention stuff that Apple did wrong to make the job easier for us. And probably the biggest reason is that instead of rolling out all this wonderful security mechanisms at once, they did it piece by piece, and they sort of made a few mistakes early on in the process. And that way, by doing so, they allow us to get access to pieces of code, and we were able to reverse engineer it, and we were able to figure out how it all worked and where the vulnerable points are and how to attack it. One of the early mistakes is in 1.0.2, the iPhone actually trusted iTunes, which we can modify easily. And at that point, we could actually send custom restore commands and jailbreak the iPhone. None of the executables were signed at that point, so you can make a simple file system alteration in your jailbroken. Another vulnerability in 1.1.1 and 1.1.2 is that everything used to run as root. So if you find a vulnerability within any sort of userland program, then you have root. And then they also left some interesting things like dev kmem, which means that we can poke and peek kernel memory and execute kernel code. So that's kind of bad. And finally, probably the mistake that first allowed Pwnage was they left the boot arguments PMD and VMD. And these boot arguments can construct a RAM disk to boot from out of anything. And that basically allowed, not out of anything, but out of any contiguous portion of memory. And that allowed us to bootstrap a RAM disk pretty easily. Because when we upload a RAM disk, it has to be, the iPhone has to store it in memory somewhere, and then signature check it, and then decide whether it wants to pass it on to the kernel based on whether the signature is correct. But even if it fails the signature check, the RAM disk is still in memory. So we can use PMD and VMD to construct a RAM disk out of that portion of memory that it temporarily stores our upload in. And then this basically allowed us to boot from an unsigned RAM disk right away and allow us to flash our first bootloaders. So, we learned a lot from this process. We now have adequate control over the iPhone's hardware to even run Linux on it. So that's basically where we are at. And I'll pass it to Muscle Nerd to describe the baseband firmware.
Big computer, I can hardly lift it. All right, I'm Muscle Nerd. I'm part of the team is sort of divided into baseband guys and S5L guys, although there's a little bit of crossover. I've spent most of the last few months on the baseband side. The goal on the baseband side is to remove the SIM carrier lock. We want it completely gone. For the first-gen iPhone, there was a good reason to do it because there weren't any markets that, other than the US, that you could use the iPhone. So there was a big push to get the first generation unlocked. The next generation, obviously, it's open to a lot more markets out there, but there's still some valid reasons, other than just the challenge of it, to get a software-based or a non-Apple-based unlock into the phone, mostly for travel purposes and just moving between the markets. The baseband in both versions of the phone is run by a system on chip called the S Gold. There's the S Gold, original S Gold and the S Gold 3. It's a full system on chip. It's completely different from the S5L over on the application side. It is connected to the S5L through some limited hardware means, some serial lines, some GPIOs, some I2S, and some DMA, which is used for audio mostly. There's some scouted radio peripherals on that side. There's some unique IDs that are permanently etched into your S-Gold and into your NOR that holds your firmware. They uniquely identify your phone, and they'll come into play a little bit later. The second generation also has GPS. That's sort of a hardware overview. Software overview, it's sort of got the same rhyme as the S5L side. There's a sequence of loaders. Some of them are, that first one, the boot ROM, is based in hardware. We believe it's masked ROM. We hope it's not, because if it's not and we do something stimulating enough to Apple, they may go off and try to reprogram the boot ROMs in the field, and that would be glorious to see, because we could reuse that ourselves. But we believe it's in masked ROM. So the boot ROM loads the boot loader, which loads the firmware, which is that humongous body of code where all of the action takes place, most of the action. So that includes Nucleus, which is a common embedded operating system, the GSM stacks, the SIM support, STK support, and all the things you'd expect from the radio. So there's this sequence, and what I'll do in the next few slides is describe a little bit more detail each of those components. Oh, I forgot these two. There's what they are calling EEPROM and NVRAM, which are really just different parts of the NOR, but they're in parameter blocks, which are smaller, so you can program them faster. These hold things that, two different things that are tied to the baseband and things that are tied to your phone. For example, your Wi-Fi is calibrated at the factory, and there's a unique set of calibration data that was determined at the factory that works with your particular RF chip, and that's specific per phone. So some of it changes depending on the baseband, and some of it never changes unless you have a different phone. Now, the big thing about the baseband, and the most irritating thing, is that there's no DFU recovery mode. And I've always been jealous of Planet Being and WizDaz and Pumpkin and all these guys, because they always had a fail-safe to basically give them a free pass to do everything you can think of to the phone. Some of us at several points have completely erased the NOR and completely invalidated the LLB and things like that. And what happens if you have an invalid LLB in there, which is that sort of that second stage, is your phone basically just rapidly flashes white and black with like these horrible looking sear marks going down the screen. And it's very scary to watch, and you think it's completely gone. And we've nicknamed it Christmas tree mode, ZF. But as bad as it looks at the time, as long as you're good with your timing of your fingers, you can always enter DFU mode and recover from that. There is nothing like that in the baseband. There are things you can do on the baseband to the NOR or to the images in the NOR that can permanently brick your phone. And on the first, I mentioned this fake blank thing. Well, I'll get into fake blank later. Okay, so now each of the bootloaders. So the boot ROM just is your basic hardware setup. It maps some of the tightly coupled memory. It maps the external NOR to come into the address space, sets up the serial. Then it goes through a sequence of checks. It goes off and checks to see if the NOR is blank, and it doesn't really check to see that the whole NOR is blank, but it looks for certain key locations to see if they're blank. If it is blank, then it allows, through the serial port, you to upload your next stage loader. If it's not blank, if the bootloader is not blank, it'll go off and load it. In the second generation, but not in the first generation phone, the serial payload that you give to the boot ROM has to be signed with an Apple certificate. That was not true in the first gen phone, and we actually made use of that not being true in the first gen phone quite a lot, because it gives you really low level, very early access to the baseband CPU. Also in the second generation phone, the bootloader itself, which would normally be the next stage of the process, is first signature checked to make sure that it's not been tampered with. And if it does not match the signed hash, then it just won't load it. It'll just stay there in the boot ROM and spin. That wasn't true in the first gen phone. The bootloader, which is this next step, is the first few NOR sectors. It has a couple different, sort of orthogonal entry points. Two of the entry points are used for normal